Good afternoon, everyone. Here I am going to present the Samarium-neodymium and oxygen isotope maps of Western Australia. Firstly, I would like to acknowledge my co-authors. This work is part of a collaboration between GSWA and Geosciences Australia. Data acquisition involved a collaboration with several university research laboratories and was funded by the Exploration Incentive Scheme. Isotope maps are spatial visualizations of extensive isotope dataset, such as samarium-neodymium and lutetium-hafnium isotopes. Such maps have been demonstrated to be powerful in imaging crustal architecture through time and show striking correlations with spatial distribution of various mineral systems, from arcing cratons such as the Yongjun craton to Cenozoic origins such as the Tibetan plateau. Therefore, isotope maps play an increasingly important role in large-scale crustal evolution research and predictive exploration targeting. The left panel here shows the spatial distribution of zircon oxygen isotope maps, color-coded by the median delta-18 oxygen values from primary magmatic compositions. The right panel shows the temporal evolution. Zircon crystallized from uncontaminated mantle-derived magmas have homogeneous delta-18 oxygen values, that is 5.3 plus minus 0.6 per mil. Low-temperature water rock interaction with surface water leads to elevated oxygen values, such as in sediment. By contrast, high-temperature hydrothermal alteration leads to lower oxygen values, such as in caldera or rift settings. In other words, zircon oxygen values are powerful in fingerprinting, reworking, and recycling of supercrustal rocks that have interacted with the hydrosphere of the Earth. The arcing Peabra and Yongjun cratons are dominated by mantle-like delta-18 values, that is 4.6 to 5.8 per mil, consistent with reworking of igneous material that had not been exposed at the surface. Some igneous rocks in the Peabra and Yongjun cratons exhibit weakly elevated zircon oxygen values from 5.9 to 6.4 per mil, which together with whole rock trace element enrichment will attribute to hydrous shulukitoids or to derivation from the shulukitoid enriched source. The Capricorn, Abilene Fraser, and Patterson origins and the Euclid basement contain rocks predominantly with elevated oxygen values from 6.5 to 10.4 per mil, suggesting significant reworking of upper crustal material that has been weathered or hydrothermally altered at low temperature. Zircon with no submantle oxygen values down to 1.7 per mil were found in the Peabra craton, the Narrow terrain, and the southwest terrain in the Yongjun, the Abilene Fraser origin, and predominantly in the Musgrave province, which suggests reworking of upper crustal material hydrothermally altered at a high temperature, likely in rift system or calderas. These new zircon oxygen isotopes have played a significant role in tracing the origins of Earth's earliest continental crust. Here we use coupled variation in zircon oxygen isotope with whole rock potassium-sodium ratios to identify two distinct groups of TDGs, represented by the red circles. The strongly sodic TDG represent the most primitive magmas and contain zircon with mantle-like oxygen isotope compositions, reflecting source rocks hydrated by primordial mantle-derived water. These primitive TDGs did not require the strong incompatible trace element enriched source, which is required by average TDG. By contrast, more potassic evolved TDG required a source enriched in both water derived from the hydrosphere, evidenced by their elevated delta-18 oxygen values, and in incompatible trace elements. which are linked to the introduction of hydrated magmas such as shulukitoid, represented by these green circles. Shulukitoid was formed by melting of metamorphized mantle lithosphere. These cartoons show how the Earth's early fascicle crust was formed in the Peeble crater. By concentrating on data from the Paleoarchean crust of the Peeble crater, we can discount a subduction setting, and instead propose that hydrated and enriched near-surface basaltic rocks were introduced into the mantle through gravity-driven convective overturn into the crust. This panel depicts continuous gravity-driven dripping of greenstone with heavy oxygen values through the entire crust column and into the mantle. During periods of lithospheric extension and dripping, primitive TDG formed through melting of arcing mafic lower crust that was already at least locally hydrated by mantle-derived water. Greenstone that dripped into the mantle released oxygen-enriched fluids and hydrated partial melts that metamorphized the lithospheric mantle. Under extension, the metamorphized lithospheric mantle melted to produce large iron lithophile element, thorium, and light rare earth element enriched hydrous shulukitoids. The shulukitoid infiltrated and mingled with ductile mafic lower crust to form the hybridized source for the oxygen-enriched evolved TDG. Our data remove many of the paradoxical impediments to understanding early continental crust formation. Sufficient primordial water was already present in Earth's early mafic crust to produce the primitive nuclei of the continents, with additional hydrated sources created through dynamic process unique to the early Earth. The neodymium isotope maps of Western Australia are based on whole rock Samarium-neodymium data from fascicle igneous rocks, which provide a window into the middle and lower continental crust. Here shows the two-stage depleted mantle model age map, that is TDM2, which provide estimates of the age of the crustal source of the igneous rocks. It highlights the distinction between arcing cratons such as Peeble and Yirgan with old TDM2 and proteroid origins with younger TDM2. It also highlights two possible rift-like structures in the Yirgan crater, such as the Karguni-Klapi rift in the eastern Yirgan and the Q rift in the western Yirgan. These maps show crustal residence time, TCR, which is the difference between the model age TDM2 and the magmatic crystallization age. It provides estimate of the length of time the source of the igneous rocks has resided in the crust. The shorter the crustal residence time, the more juvenile the crustal source is. These maps highlight that predominantly short residence times for the Peeble and the Yirgan cratons, and much longer crustal residence times in the Patsan, Capricorn, Abilene-Fraser, and Pinjarra origins, which suggest decreased juvenile crust generation in these proteroid origins. Isotope boundaries correlate well with most existing proposed terrain boundaries. These maps are directly applicable to metallurgy. For example, most giant gold deposits in WA are located on or near significant isotopic boundaries and major crustal structures. Interestingly, tephra, plutonic, and giant gold deposits in the Murchison are aligned along a northeast trending isotopic trend. Similar trend occur between the east and western Peeble and between the Yirgan crater and the Abilene-Fraser origin. These isotopically defined discontinuities may be important clues to the earliest architectural elements in Western Australia. Finally, you can access these data and the images through the GeoView and Data Software Center, so you can play with this data to create your own maps for particular areas. Have fun and thank you.